Michio Kaku's popular insight right into an astounding disclosure: the James Webb Space Telescope has perceived a requesting signal communicating from the Andromeda inestimable framework for more than a century. How we would decipher Andromeda changed into normally earthly, yet at this point, with the James Webb Space Telescope, our perspectives are definitively moving. This new discovery has sent shock waves through laid-out analysts. But what does this lovely disclosure illuminate us, and for what rationale is it creating such an uproar among region experts? Join us as we dive into the nuances of this discovery and explore the manner in which it influences how we would decipher our adjoining universe. Before we dive into the subtleties of the requesting signal, let's look at a couple of contexts. It's tremendous to understand the Andromeda galaxy. Historically, Andromeda became the principal hint that our universe stretches beyond the Milky Way. This discovery moved our ability, showing that we may also simply be a small part of the standard-size universe. Initially, the Milky Way was seen as the entirety of the universe. Early cosmologists, using limited means, couldn't distinguish the Milky Way into individual stars. This changed with Galileo Galilei, who, in the 17th century, used a telescope and discovered that the Milky Way was composed of numerous stars. This finding helped test the idea that the Milky Way was the only galaxy in the universe. The true game-changer came with Edwin Hubble. During the 1920s, using the Hubble telescope, he noticed far-off objects beyond the Milky Way, identifying them as separate galaxies, thus expanding our view of the universe. One of these galaxies was Andromeda, also known as M31. Its perception dates back to the Persian cosmologist al-Sufi in the 10th century, who observed it without the aid of a telescope. Through the 20th century, technological advancements allowed astronomers to explore further. They discovered that Andromeda was a massive galaxy of stars, much like our Milky Way, but situated around 2.5 million light-years away. The glance at Andromeda has changed drastically due to advancements in technology. Observations have shifted from ground-based telescopes to space observatories like the Hubble and now the James Webb Space Telescope. Each new tool has brought us closer to understanding Andromeda's true nature. Interpreting Andromeda's structure and composition helps cosmologists dig deeper into the universe. It also serves as a benchmark for our Milky Way, providing insights into its structure, development, and evolution. The connection between the two galaxies is crucial for understanding the future of the Milky Way, especially since they are expected to collide in around 4 billion years. Recently, the James Webb Telescope has detected a surprising signal from the Andromeda galaxy. The telescope's sensors have picked up unusual activity in Andromeda, differing fundamentally from previous observations. One key finding is the change in Andromeda's mass. Previously, it was thought to be significantly larger than the Milky Way, but new data suggests that Andromeda and the Milky Way are more similar in size than previously thought. This reshapes how we interpret the spatial relationship between the two galaxies. The James Webb Telescope has also provided clear photos and spectra from Andromeda, revealing new star formations and chemical compositions within the galaxy. This data is crucial for understanding how galaxies evolve and what conditions are necessary for life. Another significant discovery includes Andromeda's active central region. The data suggests that the supermassive black hole at its core is more active than previously thought. This activity influences the surrounding area and could affect the galaxy's overall shape and future. The telescope's findings also address the mysterious dark matter by observing the gravitational effects on Andromeda's stars. By studying these effects, astronomers can better understand how dark matter is distributed throughout the universe. These new discoveries through the James Webb Telescope have prompted further studies, with researchers around the world analyzing the data to uncover more about Andromeda's mysteries. Each finding builds on the last, providing a clearer understanding of the galaxy's history and fate, and offering a better grasp of the universe's operations. Andromeda, our closest galactic neighbor, has numerous specific features that fascinate astronomers and set it apart from other galaxies. Firstly, its size is enormous. Recent data suggests it spans around 220,000 light-years in diameter, making it one of the largest galaxies in the nearby cluster, much larger than the Milky Way. Its massive size contributes to its mass, holding an estimated 1 trillion stars, surpassing the number in our own galaxy. Andromeda's shape is another key point of interest. It has a typical spiral shape but with a bulge at the center. The galaxy consists of a protruding core surrounded by rings of dust and gas, which are sites of active star formation. These features suggest a dynamic galaxy with ongoing processes that shape its appearance and evolution. The center of Andromeda is especially exciting because of the presence of a double-ringed surge, suggesting it harbors an extremely large supermassive black hole. Additionally, Andromeda is surrounded by a halo of stellar debris stretching across many light-years. This halo is composed of stars, planetary nebulae, and globular clusters, offering evidence of the galaxy's complex evolution and history. The globular clusters, in particular, are of significant interest, with over 460 studied so far. They provide clues about the early stages of the galaxy's development and the dynamics of star clusters. Another remarkable feature of Andromeda is its collection of satellite galaxies. More than 20 smaller galaxies orbit Andromeda, some of which are being stripped of their stars and gas, contributing to Andromeda's growth. This process, known as galactic cannibalism, highlights the aggressive nature of galaxy evolution and serves as a live example of how galaxies grow and interact over time. The future and evolution of the Andromeda Galaxy are topics of substantial interest in astronomy. One key aspect of Andromeda's development is its expected transition from a spiral to a ring galaxy. Observations suggest that changes within its structure could lead to this unique shape. Ring galaxies are fascinating and usually form under special circumstances, often after a collision or near-miss with another galaxy. If Andromeda is indeed evolving into this structure, it suggests a history of interactions with other galaxies. Andromeda's fate is closely tied to its relationship with the Milky Way. Estimates suggest that in about 4 billion years, Andromeda and the Milky Way will collide and merge. While this event will seem catastrophic, it is a regular part of cosmic evolution. The collision will not involve direct crashes between stars due to the vast distances between them. However, the gravitational forces will reshape both galaxies, and gas and dust from the two will combine, leading to new bursts of star formation. This explosion of stellar creation will light up the merging galaxies, creating a spectacular astronomical event. The collision may also cause changes to Earth's orbit or axis, potentially affecting global climates. Some species may thrive under these new conditions, while others may face extinction. Furthermore, the merger could trigger the creation of new stars as gas clouds from both galaxies collide and compress. If this stellar birth occurs near the solar system, the radiation from these new stars could further impact Earth's environment, altering its climate and life. However, it's important to note that these events are predicted to occur billions of years in the future, so human life, as we know it, may have evolved significantly by then. Or, humanity may have already colonized other parts of the galaxy or universe. The findings from the Andromeda Galaxy have significant implications for our understanding of our own galaxy and its future. The comparison between Andromeda and the Milky Way allows astronomers to better understand the structure and evolution of spiral galaxies. Observing Andromeda's features, such as its spiral arms and its massive black hole, provides a reference point for studying similar characteristics in the Milky Way. These insights help refine our models of galactic dynamics and development. Additionally, the size and mass of Andromeda have direct implications for how we interpret the Milky Way. Initial assumptions suggested that Andromeda was much larger than the Milky Way, but recent data indicates that the two galaxies may be more similar in size than previously thought. This challenges our view of the Milky Way's position within the local galaxy cluster and its gravitational influence. While the Milky Way is still a massive galaxy, interactions with neighboring galaxies, particularly Andromeda, could alter its shape and dynamics. Studying Andromeda's development offers valuable clues about the processes that drive such massive changes in galactic morphology. By specializing in Andromeda's present state and predicting its future trajectory, astronomers can simulate the effects on the Milky Way, including changes in star formation, the distribution of gas and dust, and the formation of new structures. Elements of each cosmic horus, the area of space science, have talented tremendous changes thanks to mechanical progressions. From the earliest telescopes to the complex observatories of these days, each step forward has raised our data of space. The excursion initiated with the creation of the telescope in the mid-17th century. This simple device, counting focal points inside a cylinder, permitted space experts to examine the moons of Jupiter and the phases of Venus. Over time, so did the intricacy and strength of telescopes. The 19th and mid-20th centuries saw the development of enormous, all the more powerful telescopes. These permitted space experts to look further into space and to find new heavenly bodies, including Neptune. Yet these ground-based telescopes had hindrances, particularly due to environmental impedance and light pollution. The launch of the Hubble Space Telescope in 1990 marked a huge leap forward. Situated above Earth's biological system, Hubble outfitted clearer, further views of the universe than any time in recent memory. Its perceptions have achieved forward leaps in how we interpret dark matter, the age of the universe, and the development of space. Following Hubble, different space telescopes, comprising of the Chandra X-ray Observatory and the Spitzer Space Telescope, have found the universe from space. In addition to optical telescopes, radio, infrared, and X-ray observatories have expanded our vast toolbox. These units allow astronomers to detect and study phenomena that include the universe's microwave background radiation, star formation regions, and the remnants of cosmic explosion blasts. Dark matter remains one of the universe's biggest mysteries. Undetectable yet including a sizable portion of the universe's mass, dark matter doesn't emit, absorb, or reflect light, making it imperceptible by ordinary techniques. Rather, its presence is inferred from gravitational energy results on visible matter, radiation, and the large-scale structure of the universe. In Andromeda, proof for dark matter comes from the galaxy's rotational speed. Stars close to the galaxy's edge turn at comparable paces to those near the center, contrary to what would be expected if only visible matter were present. This uniform rotation rate suggests a sizable amount of concealed mass, credited to dark matter, wrapping and impacting the galaxy. Observations of Andromeda also show an enormous corona of dark matter extending far beyond the visible stars. This corona influences the movement of satellite galaxies and galaxy groups orbiting Andromeda. By studying these orbital movements, space experts can assess the mass and distribution of dark matter within the galaxy. Such studies suggest that Andromeda's dark matter halo is vast and significant, extending more than 1 million light-years from its center. The distribution of dark matter in Andromeda is not uniform. It is denser near the galactic core and becomes less dense outward, which influences the formation and development of stars and gas clouds within the galaxy. Dark matter's gravitational pull helps shape the spiral arms and affects the rate and location of new star formation. Moreover, dark matter is believed to play a huge role in cosmic interactions and mergers. The expected impact between Andromeda and the Milky Way, for instance, is also a result of the significant dark matter halo surrounding both galaxies. The elements of this impact, including the eventual state of the combined galaxy, will be significantly influenced by dark matter. New discoveries from the Andromeda galaxy have profound implications for how we interpret the universe. Andromeda's discoveries offer critical insights into galaxy development and evolution. By observing Andromeda's structure, astronomers gain insights into how galaxies expand over billions of years. This includes the development of spiral arms, the formation of essential lumps, and the role of collisions and mergers in shaping galaxies. Understanding the cycles in Andromeda allows cosmologists to develop more accurate models of galaxy development across the universe. Andromeda's findings also contribute to the refinement of the universe's distance ladder. By measuring distances within Andromeda and comparing them with those from other galaxies, space experts refine the methods used to determine astronomical scales. This is crucial for assessing the universe's rate of expansion, a key parameter in cosmology known as the Hubble constant. Additionally, the study of Andromeda's stars and chemical composition provides insights into the life cycles of stars and the distribution of elements across the universe. These discoveries help cosmologists understand the processes of nucleosynthesis and chemical evolution that occurred in the early universe and continue to take place within galaxies. Space exploration, while advancing our knowledge and understanding, also presents environmental challenges. The launch of rockets, for example, releases pollutants into Earth's atmosphere. Rocket propellants emit chemicals like chlorine and alumina, which can harm the ozone layer and contribute to atmospheric pollution. Space debris is another significant issue. Space missions leave behind particles or space junk, ranging from spent rocket stages to damaged satellites. This debris orbits the Earth at high speeds, posing impact risks to operational spacecraft and satellites. Efforts to track and remove space junk are ongoing, but the growing variety of objects in space makes this a complex environmental challenge. On planetary surfaces, contamination is a concern. Rockets traveling to different planets or moons can carry microorganisms, risking the contamination of those environments. This is especially critical in the search for extraterrestrial life, as Earth life could complicate the detection of native organisms. Space missions must follow planetary protection guidelines to mitigate this risk by ensuring spacecraft are sanitized and missions are carefully designed to avoid environmental contamination. Light pollution is a subtle consequence of space activities. Satellites and large communication networks, such as those used for global internet coverage, reflect sunlight back to Earth, blocking astronomical observations and altering the natural environment. The view of the Andromeda Galaxy provides valuable insights into the universe's structure, development, and future. By comparing Andromeda to the Milky Way, astronomers gain a better understanding of galaxy dynamics. Observing Andromeda's features, such as its spiral arms and massive central black hole, offers a reference point for studying similar phenomena within the Milky Way. This comparative method refines our models of galaxy dynamics and evolution. Furthermore, the measurement of Andromeda's size and mass challenges previous assumptions and reshapes our perspective on the Milky Way's position within the local galaxy group. Understanding Andromeda's development offers clues about the events that lead to significant changes in galaxy morphology. By simulating Andromeda's current state and predicting its future evolution, space experts can anticipate the effects on the Milky Way and produce detailed models of galaxy development. However, space exploration also presents environmental challenges, such as pollution, which must be addressed to ensure responsible investigation and maintenance of space.